Hi everybody, welcome back. In the last video we introduced the concept of momentum and change in momentum, and now we are going to further examine this in the context of a very important conservation law of nature, conservation of momentum. Conservation of momentum is an absolute conservation law. It arises from the fact that the laws of physics behave the same looking toward the left as they do looking toward the right, or up versus down, in versus out, etc. And the equation, which we'll soon unpack when we're dealing with an interaction between two objects, simply starts off that sum of p initial equals sum of p final. The total initial momentum before an interaction between multiple objects is equal to the total final momentum. Notice that I have these in bold. These are vectors. Momentum, remember, is a vector, and the vector nature is important if especially you're dealing not only in 2 or 3 dimensions where you would apply it separately for the x direction, the y direction, and the z direction. In other words, you'd have 2 or 3 separate equations depending on how many dimensions you're dealing with, but also important with respect to just the direction in one dimension, whether it's in the positive or the negative direction. In this course, we're only going to be dealing with things in one dimension. But again, if it is 2 dimensions, then each of these things you would have, instead of just what you see here, once you break it down, you would have one of these equations for each of the 2 directions. But if we're just dealing with 2 objects in one dimension, then we can suppress the vector symbols, and we would just have m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. But notice this is the result for 2 objects after these first 2 steps. We'll soon see how this applies for problems in general. First, let's examine a special case where we have one or more initial velocity being 0. That makes things a lot simpler in terms of the math, and that even makes it so that you're able to solve the problem in more than one way. So let's say you have bodies starting together. So for example, like the Donald Duck snow fight and that link that I had back here. So you set up a coordinate system and assign velocities relative to the origin. And you might even want to draw all of the objects and their associated masses and their velocity vectors just to give you a pictorial representation of what's going on. And don't forget in your givens to use correct positive or negative signs. And generally speaking, we say that right is positive and left is negative. And then you set up the conservation of momentum equation. Sum of p initial equals sum of p final. And it turns out that if the collision is elastic, you can actually set up another equation in which you don't have to know as much initial information. For perfectly elastic collisions, total kinetic energy is unchanged. But we're not going to deal with that in this class. So I do want to mention that that's true, but in this class we're not actually going to deal with problems that have that. But in any case, then you write out the terms for momentum, and you plug in the equations for momentum, and then solve for the unknown and plug in your givens. In fact, usually we like to solve for the unknown first and then plug in the givens. But in the simplest case, like what we're about to see, you might want to plug in the givens first. So here's the situation. You have a pitching machine, and the pitching machine has a mass of 50 kilograms. It's on a frozen pond, and it fires a 0.15 kilogram baseball with a speed of 36 meters per second in the horizontal direction. And the question is, what is the recoil velocity of the machine? So this whole conservation of momentum thing immediately comes into the idea of recoil, whether you're firing a weapon, whether you're using a pitching machine, firing a cannon or something like that, you're always going to have some recoil. So the idea is that they start off together at rest. The pitching machine fires the baseball, but Newton's third law says that every force results in an equal and opposite force. So as a result, the pitching machine is going to go backward as well if the baseball goes forward. So how fast does it go backward? Well, we write our givens. We have an initial velocity of both being 0, and the mass of the ball is given, the mass of the pitching machine. Notice I used the symbol PM for pitching machine, and I used the symbol B for ball. And we're given the final velocity of the ball, but we want to find the final velocity of the pitching machine. So there's our conservation of momentum equation. Sum of p initial equals sum of p final. And then we plug in what that means. So momentum of the ball initially plus momentum of the pitching machine initially equals momentum of the ball at the final plus momentum of the pitching machine finally. And then each of those you plug in an mv. Notice that the masses are different. dividing both sides by mass will not cancel the mass because the masses are different. The mass of the pitching machine and the mass of the ball are different. You're welcome to divide both sides by mass of one of the objects, just don't expect it to cancel. And in fact, we actually could have immediately canceled out, or not really canceled out, but crossed out the sum of pi term because both objects have initial speeds of 0. But we do that right here when we plug in 0. And then we're looking for the final velocity of the pitching machine, the recoil velocity as it was. So we have our numbers. In this case, we plugged in first because this is just such a simple case. So we move the 0.15 times 0.36 to the other side. That picks up a minus upon doing that. Divide the both sides by 50 kilograms. Notice we've plugged in our units. And the mass units, the kilograms, properly cancel, leaving us with meters per second at the end. So we see the pitching machine has a final velocity of negative 0.108 meters per second. It has a recoil that is of 0.108 meters per second toward the left. So we simply employed the conservation of momentum technique and solved the problem just as in a mechanical sort of way, because each step told us what to do in the next step if you're just kind of following the logic and following the algebra. And again, it is moving to the left. That minus sign matters. You got to keep it. Although if they asked you what is the final speed and direction, then you would say the final speed is 0.108 meters per second, and the direction is to the left. Now, again, we plugged in the numbers first and then solved for the variable because this was just such a simple problem that I think it made sense to do that. A lot of people are more comfortable doing it that way with the complicated problems, but chances are you're going to screw up, or at least the chances are much higher of a math mistake, particularly an arithmetic mistake, if you plug in all the numbers first before doing the algebra in the longer ones. Let's look at another example. Here you have a 7 kilogram bowling ball colliding with a 2 kilogram pin. The pin flies forward with a speed of 3 meters per second. So if the bowling ball continues forward with a speed of 1.8 meters per second, the question is, what was the initial speed of the bowling ball? So, telling you ahead of time that it's 2.7 meters per second, but now's a good time maybe to pause the video and use the same method that we just used for solving the pitching machine problem on this and see if you get 2.7 meters per second. So presumably you have now tried it for yourself. So here is one method for our solution. We have the givens, mass of the ball, mass of the pin, initial speed of the pin. I mean, you know, bowling pins start at rest. They better start at rest. And the final speed of both the ball and the pin are given. They are different. So use conservation of momentum. Sum of pi equals sum of pf. What does that mean? Well, momentum of the ball initial plus momentum of the pin initial is equal to those at the end as well, added together. Now, different objects might have different momenta, but if the ball's momentum ends up being less, the pin's momentum ends up being more. Well, the pin starts at rest, so we crossed out that term. And again, using our bad algebra student technique, this time we're just going to plug in the numbers first. And we can, in this case, we can work it out. We have a 7 times a 1.8, that's going to be a 12.6. A 2 times a 3 is a 6, so adding those together gives 18.6. And then we can divide that by 7. And upon doing that, we get about 2.7 meters per second. It's actually like 2.71 something, if I remember right. Okay, so what about doing it the kind of good algebra student technique? I mean, in this case, we were kind of borderline on the problem being a little more complicated. We only had one zero term in this case. So let's see how it looks using our preferred method. So again, of course, we write down our givens. We have conservation of momentum, sum of pi equals sum of pf. That means just for every sum of pi, you put in a term for each object. We have a ball and we have a pin. Cross out terms that are 0. But this time we solve for the initial velocity of the ball first. So we simply divide both sides by the mass of the ball, because the velocity of the ball is just in this one term. So if if this wasn't 0, we would subtract it from both sides first, and then we would divide both sides by the mass of the ball. And now we have our equation. We're ready to plug in our numbers, and in one fell swoop, we get 2.7 meters per second, just like before. Okay. Now, I should mention that in the case of elastic collisions, you're dealing with a situation where the objects will kind of bounce. I mean, think about billiard balls, super balls, that is, those bouncy balls. Also, for that matter, air molecules between each other and the walls of a container. In those collisions, both momentum, which is always conserved, and kinetic energy are conserved. But again, we're not going to work on those calculations. But if you were, for example, if you were taking AP Physics 1, then you would also have a separate equation that says sum of K initial equals sum of K final. And you would have, after the next step, you would eventually have a 1/2 M1 V1 initial squared plus 1/2 M2 V2 initial squared equals that same stuff final. And then you would have the system of equations that you would use to solve for both unknown velocities. But here we're not doing that in this class. We're just dealing with one unknown velocity. So there are also perfectly inelastic collisions. In a perfectly inelastic collision, there isn't any bouncing at all. A perfectly elastic collision, they bounce perfectly, so to speak. But in a perfectly inelastic collision, they stick together. In a manner of speaking, we just solved a couple, or at least we solved one problem like that. The pitching machine problem was kind of the inverse of a perfectly inelastic collision. Except, in other words, if you reverse initial and final, imagine the ball coming back to the pitching machine from the opposite direction, then they would both come to a stop if they stuck together. Well, inelastic is a situation where the final result is the objects sticking together. For example, like a meteor collision with Earth most of the time. A stupid ball, in other words, you have a ball that's like filled with beans or something like that, you drop it and it doesn't really bounce from the floor. Or putty hitting the floor. So you might wonder what happens to the kinetic energy of all the molecules that are in there. And the answer is that it's usually lost as heat, and sometimes as deformation or as sound or stuff like that. Deformation being going into elastic potential energy of the molecules between each other or the material itself. Okay, anyway, let's take a look at an example. Let's say you have a perfectly inelastic collision between a large car and Superman. If the car with a mass of 1,800 kilograms is going at 27 meters per second, we'll presume toward the right, and Superman has a mass of 100 kilograms and is standing still, the question is, what is the velocity of the wreckage after the collision? So, okay, well, we have our givens. Notice that the initial velocity of Superman is listed as 0. S is for Superman, C is for car. And since this is a perfectly inelastic collision, that means they stick together at the end. Well, what does that mean? That means their final velocities are the same. The final velocity of the car is the same as the final velocity of Superman. In other words, we'll just call it V sub F. That's very useful because we can factor it out. So, here we have the steps, and soon I'll just lay them out step by step, but it's really the same stuff as before. You have the same, you write your givens, you have your conservation of momentum equation, you have the result of that between two objects, you cross out something that's 0, but the only thing here is we realize that one of our final velocities and the other final velocity, they're both the same. So we call them the same thing and allow them to be factored out. Okay, so let's see how that looks step by step. Okay, so between the car and Superman, again, we start off with conservation of momentum, sum of pi equals sum of pf. What does that mean? Well, there's a car and there's Superman. So you need car initial and Superman initial, and car final and Superman final for each of their momenta. So there's a momentum for each of them, each initial and final as well. For every momentum, we have an MV. We cross out a term that we know to be 0. If it's not moving, it has no momentum. Superman started off not moving, so he had no initial momentum. So we crossed it out. In fact, we could have crossed it out right here and just skipped straight to PCI equals MC, VCI equals, etc. And keep in mind that the final velocity of the car and the final velocity of Superman are the same because we're told it's an inelastic collision. So I plugged in a VF for both of those. Because after all, they're the same. It's perfectly inelastic. And that's useful, again, because going from this step to here, I'm able to factor it out. There's only one number now that I need to solve for. That's VF. So I divide both sides by mass of car plus mass of Superman to get final velocity of car and Superman. And you get 25.6 meters per second. And that translates to about 57 miles per hour. So this collision actually had very little effect. Of course, Superman, being the Man of Steel, supposedly braced himself really, really well to cause the car to end up being a lot slower than that, with that extra momentum going into all the rocks and everything in the ground that are bracing Superman. Okay, how about another example? Consider a weasel running after a chicken. Sneaky, sneaky, sneaky. So the weasel runs at 5 meters per second, we'll presume toward the right. If the 2.25 kilogram chicken is traveling at 2 meters per second, also toward the right, it's trying to escape from the weasel, who has a mass of 0.7 kilograms. Calculate the velocity of the chicken plus weasel system after the weasel catches the chicken. So we presume that the weasel grabs onto the chicken and makes mincemeat out of it. Well, mincemeat isn't what you would have for roast chicken, but anyway. So we have our givens, masses, initial velocities, and we're told the weasel catches the chicken, so we presume this is an inelastic collision. So sum of pi equals sum of pf. For two objects, that's weasel initial momentum plus initial momentum for the chicken equals weasel's final momentum plus chicken's final momentum. So there we go with that. And then we plug in mv for everything there. In this case, nothing is zero. But we do note, again, that the weasel and chicken have the same final velocity because they stick together. The weasel grabs onto the chicken. Okay, so at the end what we have here is m weasel v weasel initial plus m chicken v chicken initial equals, open parentheses, m weasel plus m chicken close parentheses times v final. So divide both sides by the total mass. M weasel plus m chicken will isolate for the final velocity. So that's what we will do right here, dividing both sides by mass of weasel plus mass of chicken. In other words, the total mass of the thing that's moving at that speed. And then plug in the numbers. And there we go. And we get a result of 2.71 meters per second. And again, presumably toward the right, but here we've kind of gotten sloppy and dropped all of our signs because everything's going in the same direction. Okay, so those are two problems involving inelastic collisions as well. And FYI, if you're dealing with two dimensions, you would do exactly what we just did, just as I said before, except you would have to break it into, after your sum of pi equals sum of pf, you would say, okay, sum of pi in the x direction equals sum of pf in the x direction, and sum of pi in the y direction equals sum of pf in the y direction. And you would keep going for each of those directions. So you would do the same thing we just did, but twice. But we won't actually do that. Instead, we are going to discuss the concept of impulse and how an impulse on one object will change its momentum and therefore its velocity. We'll do that in the next video. I hope to see you then, and thank you for watching.